All right, Chalk Talk fans, better get ready because this episode's gonna be hot. That's right, better crank up the cooling fans, dust off the heat sinks, and fire up the ferrofluid heat pumps, because the mercury is rising. How hot will it get, you ask? Well, that is the question, isn't it? After all, in electronic design, we're always worried about the effect of heat. As the temperature rises, our electronics can start to get, well, temperamental. And nobody wants that. The first step in managing our thermal situation is measurement. We need to know just how hot a thing is before we can take action. Hi, I'm Amelia Dalton, host of Chalk Talk. There are numerous situations where we need to measure temperature, from controlling boilers and furnaces to just making sure our electronics don't burn themselves up. But temperature measurement can be a tricky proposition. My guest today is John Austin from Microchip Technology, and we're going to chat about thermal management. Before we get started, don't forget to click that link. There you can find out even more information about thermal management solutions from Microchip Technology. Hi, John. Thank you so much for joining me today.
Hi.
So it seems like just about everything we design has some kind of thermal management issue we have to deal with. Where do you see thermal management being used today?
Well, really, thermal management is everywhere. It's across many markets and many applications. In industrial, you can think things like boilers and furnaces. Consumer PC servers have become very popular for thermal management in the past 5 or 6 years. Automotive and aerospace, petrochemical is the largest industry. To give an example, a few weeks ago, my water heater, I couldn't get the pilot to light, and there's actually a thermocouple that sits in the flame that controls the gas so that, you don't have an accident by filling your garage full of gas. So even in consumer applications that you would think pretty high volume, and there's thermal management.
Very cool. So, John, what are the benefits of adding thermal management to my system?
Really, there are a lot of benefits. You can improve your quality of your product, the reliability of your product. So many things degrade over temperature and over time. It can extend the product life. It can improve product performance. For electronics specifically, characteristics of silicon changes over temperature, and you can calibrate and accommodate for certain changes over temperature by using thermal management and monitoring temperature. You can provide consumer safety. So there's a lot of value in adding thermal management to many products.
Excellent. All right, John, let's put our nerd hats on and dive in and talk about some of the options we have for thermal management.
Okay, so outside of silicon ICs, the most common are thermistors, thermocouples, and RTDs. They've been around for a long time, these technologies. Thermistors generally people think of for low-cost, general-purpose type applications. The main benefit to a thermistor solution, for the most part, is cost. The drawback to a thermistor, so if you look at the graph, you can see that the linear range is right around freezing to about 50 degrees C.
Okay.
So I can get a fairly accurate measurement in that linear range without adding a lot of additional signal conditioning, which adds cost and complexity to my solution.
Yeah.
Another drawback to a thermistor solution is the fact that it requires a constant current source, so it consumes a lot of power. There are definitely benefits to a thermistor. You can get a pretty accurate solution for fairly low cost over a narrow temperature range, but again, they consume a lot of power.
Okay, so thermistors are our kind of base level solution. What if I need more accuracy?
For more accurate solutions, you can use an RTD. The drawback is RTDs are somewhat expensive. They're fairly complicated circuitry. They require precision instrumentation, high resolution data conversion. I have a sample circuit on the slide. You can operate them over a fairly wide range, about minus 200 degrees C to about 800 degrees C. And you can see this is actually out of a Microchip app note, but on the right you can see a graph of accuracy versus temperature, and it's well within 0.1 degrees C accurate.
Yeah.
So that's the benefit. Again, these require a current source. It's a resistive element. RTD is resistive temperature detector. So they consume power. There has to be a lot of care taken for the resistor value that's chosen for the circuitry, because it can cause self-heating, which can give you a lot of inaccuracies.
Right.
And again, RTDs are very expensive. So it's a fairly complicated solution. It requires some expertise
Okay.
and costly, but the benefit is you can get a highly accurate solution over a pretty wide range.
Okay, so I can get more accuracy, but I have to pay for it. But what if I have to measure things in a really harsh condition?
Yeah, thermocouples have been around for a long time. They can measure temperature from about minus 400 C to about 1250 C.
Wow, okay.
Again, it's a fairly complicated solution. So on the slide, you see a typical discrete solution. The 2 op amps in the front with R1s connected is basically a differential front end, so I have to have precision matched resistors. That feeds into a differential amplifier, where again, R2s have to be precision matched to not cause offsets and errors. I need precision data conversion. And then I need cold junction compensation, which requires a precision temperature sensor. That temperature sensor could be basically a thermistor, it could be an RTD, it could be another thermocouple, it could be a silicon IC, it could be whatever I want it to be, but it has to be a precise temperature measurement at the cold junction. And I need that to calculate the equations. So there's 8 standard thermocouples that have unique high order equations to calculate what my temperature is based on the voltage I'm reading at the cold junction.
Okay.
So it requires a microcontroller or some math engine to do the math. These can be expensive. Depending on the accuracy you need, it can be a fairly low-cost solution, $1, $2 solution, up to tens of dollars or even hundreds of dollars, depending on what I need, and into the signal conditioning. They're available, been around for a long time. Again, it requires a lot of expertise and many different design facets to implement the solution.
Gotcha.
So that would be the biggest drawback to that solution.
Okay, so how does Microchip fit into this picture?
I'm glad you asked. So Microchip makes integrated circuits. So we have a broad family of silicon ICs that monitor temperature and do a lot of other functions. So we kind of categorize these in 4 categories. We have a voltage output. We have what we call in the industry a temperature switch, which is a logic output. It asserts a logic signal when a threshold is reached. We have a digital output, or really it's a digital interface, so I2C or SPI. And then we have many integrated solutions that do things like, for example, we have a thermocouple conditioning IC. They interface to other things externally and do the signal conditioning and computation to give the customer a simple solution for a thermocouple or for a remote diode.
Okay, so voltage output is the first one. Let's start off talking about that one.
Yeah, so voltage output temperature sensors, you can see the 2 graphs. I mean, basically, the voltage output temperature sensor is very similar to a thermistor in function.
Okay.
Meaning it gives you a voltage output that is related to the ambient temperature.
Ah, okay.
For the voltage output, where they're useful over a thermistor is the fact that it's a linear output. So if you remember the curve a few slides back where the thermistor was only linear in the range of 0 to about 50 degrees C,
Yeah.
the voltage output ICs are linear from minus 40 to 125. Or depending on the part, there are probably parts in the industry that are minus 55 to 150.
Okay.
They're fairly a low-cost solution. They're offered in small packaging. They don't require the current excitation. So where I might have a thermistor that is consuming tens of milliamps all the time because I have a constant current source, these are in the microamp range. I mean, they're very low power consumption. So those are the benefits. Some of the drawbacks to these, you're kind of limited on packaging. We offer parts in SOT23 or SC70, where a thermistor, you can get a lot of different packaging and customized packaging.
Okay, so what about that second one? Temperature switch, I believe?
Yes, the temperature switch, again, it's the logic output. You can see the graph on the right kind of shows you the functions. So the way these work is as temperature increases, you pass a predetermined threshold, which would be the top black line. And at that point, the output would assert and tell either the processor that you had passed that threshold, or it could even be used like in the application where when that threshold is crossed, it drives a fan. So in the example, it's actually the output is a MOSFET and it's driving a fan.
Okay.
So it would turn on a fan or could turn on an LED as an indicator or something like that. But it will remain asserted until you come back across that temperature threshold minus the hysteresis, and then it will deassert. So basically it just ensures you're either above or below a specific temperature. So you can think of these as a little bit more integrated as a voltage output device, because it adds that functionality of being able to select the temperature that you monitor. They're restricted to about minus 55 C to 150 degrees C, but they're very cost-effective, small solution that can be used to improve your product.
Okay, and then the next one you had on the list was digital output?
Yeah, so when I say digital output, they're either an I2C or an SPI interface. I have a graph on there that just gives you an idea of how these work. These devices can be very accurate solutions. There are devices on the market that are below a half a degree C accurate over a wide range from probably minus 20 to about 100 degrees C or 110 degrees C. The nice thing about these is I can, for example, if I have an I2C interface and I pick an I2C part, I can have multiple devices in my system that I can communicate off of a single bus.
Yeah.
So that's kind of what's illustrated in the top. So I can have, 8 of these in my system. The accuracy is specified as low as 0.2 degrees. Again, I can monitor various locations on a bus. And then there's high levels of integration, so the fact that you can interface to this through an I2C or an SPI interface allows you the ability to program, and it allows us the ability to put in features that you can program that can benefit your solution, your end equipment. So many of them have things like programmable alerts, so a user can set temperature windows that they want to make sure their system stays within a certain temperature.
Yeah.
Critical temperature thresholds. Many things are integrated in these, like digital filtering, so reduce effects of EMI if I'm in a harsh environment. And there's a lot of different power savings modes that customers can set up with these type of devices, where I can go into shutdowns and things like that to conserve power. Again, the biggest drawback to these solutions, since they're silicon, is the temperature range. You're really restricted to about minus 55 to 150 degrees C, which is the limitation of silicon.
Okay, that's something I could easily drop into just about any kind of embedded design. Do you have something that can do a bit more of the heavy lifting for me?
Yeah, so we have what we call integrated ICs. And really, these are conditioning ICs for other thermal management solutions. For example, the MCP 9600. So where that's a very complicated analog and digital solution from a design standpoint, it requires a lot of expertise in analog and mixed signal design. This device integrates basically all the signal conditioning. So it has the instrumentation front end, it has the high resolution data converter, it has the cold junction compensation integrated into the device, and then it also has a math engine integrated that is pre-programmed with all the firmware to do the math for the standard 8 thermocouple types.
Okay.
So there's integrated solutions that offload that development effort and design effort from the customer. There's a lot of integrated features as well, a lot of power saving modes in the device. There's a digital filter, so for thermocouples, for example, they are in many instances being in very harsh environments where the leads are very long, like I mentioned, like feet. So they can pick up EMI and things out of their surroundings. So filtering is pretty important. This helps minimize that effort on the customer end. There are many different programmable alerts, and then it's I2C, so you can have multiple on a bus. And so the benefit to these types of devices really is reducing the customer's design effort and ultimately improving their time to market.
Right.
And then we also have remote diode monitors. I also include these in this category for the fact that they use an external element as the temperature sensing element. So these devices monitor just standard diodes, so less than a penny. And they do all the signal conditioning to determine the ambient temperature based on the VBE voltage of the diode.
Okay.
They can monitor up to 8 zones. Each one has an internal temperature sensor, and they monitor a remote diode. And what's nice about these is that they account for things like lead resistance and trace resistance. So it has what's called resistance error correction. It guarantees that up to 12 inches away, that's a pretty big PCB. To be 12 inches away from the part, 12 by 12 by 12. It will internally compensate for that lead resistance and line resistance. Also useful in things like off-board type applications. You know, you see thermistors a lot in today, especially in higher end refrigerator freezers, things like that, to monitor different locations.
Oh, yeah.
In the refrigerator freezer. I think that's an ideal application for a part like this. And then again, they come with other features, so temperature alerts, many power saving features, and some of these also have fan control features where they'll control external fans based on the remote diode temperatures.
Very cool. All right, John, this was quite a bit to take in this morning. Can you give me a quick recap?
Yeah, really the benefits of adding thermal management are to improve quality and reliability and performance. It can extend your product life. One thing to take away is that all sensor technologies have trade-offs, goods and bads. There's reasons why you'd use one over another.
Sure.
Off-the-shelf solutions can minimize design effort and time to market. So a lot of the silicon ICs solutions, one of the main benefits is you don't have to do the work yourself. A lot of them offer just plug-and-play solutions like the MCP 9600 or many of the remote diode solutions that Microchip offers today.
Excellent. Well, I think that's all I have time for today. Thank you so much for joining me, John.
Thank you.
And before we go, you didn't forget to click that link, did you? There you can find out more information about thermal management solutions from Microchip Technology. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to EE Journal's YouTube channel or check out the on-demand section of eejournal.com.